Hi, this lesson is about exponential functions. But before we talk about exponential functions, we're going to review some of the rules for exponents. So the rules are here on the left-hand side, and there'll be an example or two on the right-hand side. So the first rule is that x to the 0 power is equal to 1. So your base is x, but your base could be pretty much anything, a variable or a number. So here are a few examples. 3 to the 0 power equals 1. 1/5 to the 0 power equals 1. And you could have variables combined with coefficients. 2xy to the third, the whole thing to the 0 power, also equals 1. The second rule says that if you have x to the n times x to the n, the way you combine those two expressions is to add the exponents. That's x to the m plus n. So if I had x to the x to the fifth times x to the third, when you add the exponents 5 and 3, you will get x to the eighth. The third rule states that if you have x to the m raised to the nth power, the way that's simplified is to multiply the two numbers m and n. So if I had x to the fourth raised to the fifth power, I would multiply 4 times 5, and I would get x to the 20th as my answer. The fourth and fifth rule are similar. That is a way to eliminate a negative from an exponent. So if I have x to the nth power, the base goes to the denominator. So in other words, you take the reciprocal of the base, and the exponent changes to positive. So it's 1 over x to the nth. And the opposite is true when your exponent is in the denominator and it's negative. You bring the x up. Again, take the reciprocal of 1 over x, it becomes x, and my exponent changes to positive. So examples are here. X to the negative 2 equals 1 over x squared. 1 over x to the negative 7 equals x to the positive 7. If I had a fraction, suppose I had 2/5 to the negative 1, the whole thing in parentheses, raised to that power, that would be corrected by just taking the reciprocal of that, and 5 over 2 raised to the positive 1 power is just 5 over 2. Okay, in addition to the rules for exponents, we do need to also remember how to rewrite a radical as an exponential expression, and vice versa. So every radical can be rewritten as an exponential expression by using this definition. So if you have the nth root of x to the mth power, that is the same as x to the m over n, where the n is the denominator in your fraction, but that is the root. The only time you don't write an n is when it is a square root. When you don't see a little number in the corner of your radical, it is assumed to be 2 for a square root. But any other radical, like a cube root, a fourth root, fifth root, etc., you would have to put the corresponding number in the corner where the n is. So, for example, if I wanted to rewrite the cube root of x, that is the same as x to the 1 over 3. And if I wanted to rewrite the fifth root of x of a to the second, that is equivalent to a to the 2 over 5. And that's just applying the definition that you see above in the box. Here, it's a square root. So like I said, you have to assume there's a little 2 here, even though you don't see it. So the square root of y is the same as y to the 1/2. And here I have the square root of a plus b. A plus b is inside of the square root symbol, so that is the same as a plus b in parentheses raised to the 1/2 power. Okay, so we're going to be using the rules for exponents for some of the work that we'll do, as well as this other rule of converting a radical to an exponential and vice versa. We'll go back and forth. So the exponent, the number that the base is raised to, can be any real number. It could be rational or irrational, and it could even be a variable. So for something like this, you would need a calculator. because square root of 3 is an irrational number. So if you did 5 to the square root of 3, it would be approximately equal to, that's what those curly equal sign means approximately equal to 16.241. So that was rounded. So if you have a problem like that presented to you in the homework, make sure you follow the directions for whatever place value they want you to round. I rounded this one to the thousandths place. But something like this, 5 to the third, you wouldn't need a calculator for that because you're just multiplying 5 times 5 times 5, which gives me 125. And 5 to the negative 2, well, I'm going to use one of the rules that we talked about earlier. 5 to the negative 2 means that the 5 goes into the denominator. So this is 1 over 5 squared. But when you square the 5, you get 1 over 25. On the next line, there are a few more examples. Here my exponents are variables. So 3 to the x times 3 to the y. 3 is the base. And so the rule is just that you add your exponents. So I have 3 to the x plus y. X and y are not like terms, so you really can't combine them more than what you see here. 3 to the x raised to the y, that was the third rule I discussed earlier. You multiply the exponent, so that's equal to 3 to the x times y. Then I have 4 to the 1/2 power. Remember, when you have an exponent that is a fraction, that could get rewritten as a radical. So that's equal to the square root of 4, but square root of 4 is a perfect square, so that's equal to 2. And when I do 9 to the negative 1/2, well, there's another negative exponent. So this becomes 1 over the square root of 9. But the square root of 9 is a perfect square, so this is equal to 1 over 3. And then I have 25 to the negative 3 over 2. So this negative means this ends up in the denominator. It's 1 over the square root of 25 raised to the third power. Square root of 25 is 5, but when you cube that, you get 1 over 25. So this is a combination, all these examples were a combination of different rules that we discussed at the beginning. So what's an exponential function? It's a function where the exponent is a variable, such as y equal b to the x. But your base has to be a positive number and it cannot equal 1. So it could be any positive number except for 1. We call b the base. The x-axis in an exponential function is a horizontal asymptote to the graph. And remember, the x-axis is stated as the line y equal to 0. So the reason why b has to be greater than 0 is because if your base was negative, then you wouldn't get a real number result for any radical. So for example, the square negative 9 to the 1/2, that would be the square root of negative 9, which is an imaginary number 3i. So that's why your base has to be positive so that you end up with real number results when you evaluate it. And b cannot equal 1 because if it was equal to 1, 1 to any power, y would be y equals b to the x. So if your b is 1, it would be y equals 1 to the x. 1 to any power is just 1. Y equal to 1 is a constant. It's actually a horizontal line. It's a linear function. So that would not be an exponential function. It would have some of the attributes of a line. Okay, so the following are examples. Some are exponential, some are not. So y equal to 2 to the x, that would be exponential. My base is 2. Y equal to negative 2 to the x, that is not exponential. My base is negative. It is not greater than 0. The third one, y equals negative 2 to the x, that is different than the line above it. When y is equal to negative 2 to the x, the base is 2. And so it's a positive number. And then whatever result you get when you evaluate 2 to the x, then you would take the opposite sign afterwards. So that is also exponential. The square root of 2 to the x is also exponential. Your base is positive and it's not equal to 1. And 2 to the negative x, this is also an exponential function. Remember, your exponent can be anything, positive, negative, or 0. And this is the same as 1/2 to the x. 1/2 is definitely a positive number and it is definitely not equal to 0. So that is also exponential. So they are all exponential except for the second example. So we're going to simplify a few exponential expressions by just plugging in numbers for x and evaluating it. And that will help us later on when we actually graph an exponential function. So I have y equals 2 to the x for x equal to 0, 1, 2, and 3. So you just have to plug in 0 first. And again, this was the first rule I gave you. 2 to the 0 power is 1. When you plug in 1, 2 to the first power is 2. When you plug in 2, 2 squared is 4. When you plug in 3, 2 to the third is 8. So you can see as your x's increase from 0 to 3, your y's increase from 1 to 8. So the y's increase much faster than the x's do. Okay. Part B of this example is similar. I have a different exponential expression, 3 to the x, but I'm inputting different values of x, -3, -2, and -1. So 3 to the -3 means you have to take the reciprocal of the base. It's 1 over 3 to the third, which is 1 over 27. When I plug in -2, it's handled in a similar way. It's 1 over 3 squared, which is equal to 1 over 9. And when you plug in -1, you just take the reciprocal. This is 1 over 3 to the first power, so it's just 1/3. So here I have y equal to 9 to the x. This time I'm inputting some fractions. I have x is -1/2, 0, 1/2, and 3/2. So 9 to the -1/2 is the same as 1 over 9 to the +1/2. But remember, a fraction as an exponent becomes a radical. That's 1 over the square root of 9, which gives me an answer of 1/3. When I plug in the next number for x, that's 0. Remember, anything to the 0 power is 1, so 9 to the 0 is 1. When I plug in the fraction 1/2, it's similar to the first one here, except I don't have to take the reciprocal because my exponent is positive. So this is just the square root of 9, which is equal to 3. And when I input the last fraction, 3/2, this is the same as the square root of 9 to the third power. The square root of 9 is 3, and when you cube it, you'll get 27. So that's just a few examples of how to evaluate an exponential expression. For the next few examples, a calculator would be needed. You wouldn't need a calculator for any of the last few examples I did in part A, B, and C. But here my exponents are decimals and a radical, so not just a fraction or an integer. So when I plug into a calculator 5 to the -0.2, again, I rounded it here to the thousandths place, which is 3 decimal places. That is approximately equal to 0.725. When I input square root of 2, 5 to the square root of 2 is approximately equal to 9.739. And when my input is 3.05, 5 to the 3.05 is approximately equal to 135.475. So some calculators have a little caret key, which means raised to the, so you would say like 5 to the square root 2. That's what you put in that one. Other calculators have a key that looks like this, x to the y, where it would allow you to input the 5 as that would be the x and the root 2 would be the y. So if you're not sure how to use whatever calculator you're using, please refer back to the manual, and a lot of times the manuals are online. You can look up how to input an exponent. So now let's talk about some of the characteristics of an exponential function, what it's going to look like when we graph it. So for any exponential function, the domain is going to be all real numbers, and your range will be all positive numbers. Number 2 says that the x-axis, or the line y equal to 0, is an asymptote, and it is going to be a horizontal asymptote of an exponential function b to the x. The third characteristic says that as x increases, b to the x also increases as long as the base is greater than 1. But then the opposite is true. As x increases, b to the x decreases when your base is between 0 and 1. So that could be like a base of a half or a base of 0.3. And then raised to any power, your graph would be going downward from left to right. The graph of b to the x has a y-intercept at 0, 1. So no matter what b is, whether b is greater than 1 or between 0 and 1, when your input is 0, anything to the 0 power is 1. So that's why the 0.01 is on the graph. Okay, so here we want to graph y equal to 2 to the x, where x is -2, -1, 0, 1, and 2. And so we compute our y values by just replacing all of these x's in here. So we did that before for some of these numbers. When you plug in -2, you'll get 2 to the -2, which is 1 over 2 squared, which is why we get a fourth. When you plug in -1, you get a half. When you plug in 0, you get 1. When you plug in 1, you get 2. When you plug in 2, you get 4. So if you were to plot all those points on an xy plane, you get the graph that's here on the right. So here's the -2 1/4, here's 2, 4, and all the ones in between. The one right here, 0, 1, that's your y-intercept. That's where it crosses the y-axis. And so a summary of some of those characteristics are here on the right side. Your domain is all real numbers. Your range is all positive numbers. Again, if you read the graph from bottom to top, your graph is in quadrants 1 and 2. There's nothing in quadrants 3 and 4, so your range is all positive numbers. The horizontal asymptote is y equal to 0. Remember, that's the x-axis. So you can see here, this is getting really close to the x-axis, but it's never going to quite touch it. When you read the graph from left to right, it is increasing, it is going up. I have a y-intercept at 0, 1. And so some of this notation we've seen before. Let's just practice it, how to read it. As x approaches -infinity, your f of x is approaching 0. So what this means is as your x's become more and more negative, your y's get closer and closer to 0. That's this part of the graph. And then the second statement says that as x approaches infinity, f of x approaches infinity. So as you go further to the right, your graph gets, or your y's get bigger and bigger. Okay, so now we're going to graph y equal to 1/2 to the x. So that's an example where your base is between 0 and 1. In that case, all of the attributes are the same, except your graph will be decreasing instead of increasing like your last example. So remember, 1/2 to the x can be also rewritten as 2 to the -x. They mean the same thing. So when you plug in a negative number, you get 4. So 1/2 to the -2, again, you'd have to take the reciprocal. That becomes 4. -1, that becomes 2. 0 is 0 is 1. Again, that's your y-intercept. At 1, it's a half, and at 2, it's a quarter. So when you plot these all, you get the graph here in green on the right. So your y-intercept is this blue point on the y-axis, and you can see that the graph is going down from left to right. So again, just to review some of the attributes, your domain is all real numbers, your range is all positive numbers, your horizontal asymptote is the line y equal to 0. Here you can see graph is getting close to the x-axis, that is the line y equal to 0. The graph is decreasing over all real numbers. You have a y-intercept at 0, 1. And then these two state that as x approaches negative infinity, as you go that way, your f of x goes to infinity. But as x approaches infinity, your f of x is going towards 0. Okay. So let's move on. An exponential function graph where the base is greater than 1 will look similar to the graph of y equal 2 to the x. That's the one that I plotted earlier, the one up here. The graph will be going upward from left to right. But when your graph is between 0 and b, then your graph is going to look more like, between 0 and 1, then your graph is going to look more like the second one. Okay, so here we're going to do a little review of things we talked about in chapter 2, that is shifting. So it says to describe the shift of y equal to 4 to the x plus 2 from the function y equal to 4 to the x. So think of this as the parent and this is the shifted function. Then state the horizontal asymptote and the y-intercept. So when you're affecting the x, you are going to be shifting either left or right. When you're adding, that means you're going left. So this will be a horizontal shift 2 units to the left. Since you're shifting left, your horizontal asymptote has not changed. It is the x-axis, it's the line y equal to 0. And the y-intercept, well, that's when you plug in 0 in here. For x. So I have 4 to the 0 plus 2. That's equal to 4 to the second, which is equal to 16. So 0, 16 is the y-intercept on the original, on the shifted graph of 4 to the x plus 2. The next one is a different type of shift. I have 3 to the x minus 2. That's going to be a vertical shift. So, and that's going to be a vertical shift down 2 units, vertical shift down 2 units. And since I have shifted vertically, that means my horizontal asymptote has also gone down by 2 units. So remember, the horizontal asymptote is typically y equal to 0. When you shift down, the new asymptote is at y equal to negative 2. And when you plug in 0 in here, you'll get y equals 3 to the 0 minus 2. That is 1 minus 2, which is equal to negative 1. So 0, negative 1 is your y-intercept. Okay. Here we want to state or find the difference quotient for the function f of x equal to 10 to the x. So that, again, goes back to a concept from chapter 2. There's a definition for a difference quotient. And so that means that you plug in x plus h where the x is first minus f of x all over h. So the 10 to the x plus h can be rewritten using your rules for exponents as 10 to the x times 10 to the h, because when you multiply, your exponents add. So we're going backwards. You're given the sum of two exponents. We wrote it as a product. And that then allows us to factor out a common factor, which is 10 to the x. So I have a 10 to the x here and 1 here. So I'm left with 10 to the x, parentheses 10 to the h minus 1, all over h. Okay, so here we have a word problem regarding exponential functions, and it's called problems on compound interest. So in order to use the formula, we have to understand all the components of the formula. It says that compound interest is calculated by A of t equal to P times 1 plus R over n to the n times t, where A of t is the amount after t years. So if you're investing money, the A of t is how much you have after t years. The P is called the principal. That is the amount that you invest. That's the original amount that you invest. The R is the interest rate. So that is a percentage. Percentages always get converted to either fractions or decimals. We typically use decimals. N is the number of times that the interest is compounded. That means how many times in a year is the interest going to get added to your original principal. The more times the interest is compounded, so the higher the N is, the more you'll have at the end. And T is the number of years that you invest your money. So here we have a problem, and the first step is to identify all the parts of this formula. So it says if $10,000 is invested at a 3% interest rate per year, compounded semi-annually, find the value of the investment after 5 years. So the amount invested is your principal. So the P is $10,000. The interest rate is 3%. So my rate is 0.03. It's invested for 5 years, so your time is 5. And semi-annually means twice a year, so your N is 2. So now that we know what all of the variables represent, now I can solve for A of t, which in this case would be A of 5. And so plugging it into the formula above, that's going to be 10,000 times 1 plus 0.03 divided by 2 raised to the 2 times 5. Remember, 2 is your N and the 5 is your time. And when you put that all into a calculator, this would definitely be done with a calculator, you get that your new amount after you invested for 5 years at 3% interest, semi-annual compounded rate, compounded interest, you get $11,605.41. Okay, here's another one. An amount of $2,000 is invested at an interest rate of 12% per year. Find the amounts after 3 years if interest is compounded annually and quarterly. So we're going to calculate the amount that we made on this investment, the total value of the investment amount that was earning interest, two different ways. With your interest compounded annually, meaning once a year, so here N would be 1, and then again with your interest compounded quarterly, which here your N would be 4. So when N is equal to 4, that amount should be higher than just N equal to 1. So annually would be A of 3 is equal to $2,000 times 1 plus 0.12 over 1 to the 1 times 3. And again, when you put this into a calculator, you would get $2,809.86. And then quarterly would be almost the same, except here you'd be dividing by 4. And here you'd be multiplying 4 times 3. And when you compute that, you get $2,851.52. So more is gained when your investment, when your interest is compounded quarterly than when it is compounded annually. If this was changed to monthly compounded interest, then N would be 12. So you would be dividing here by 12, and here you'd be multiplying 12 times 3, and this amount would be even higher. So that's it for this lesson. Good luck.